Hello students, welcome to the second session of our first module in our subject CFF, compressible fluid flow. So students, in the previous session I have told you that there are four basic physical phenomena you have to be thorough. First one was mass conservation. Second, momentum conservation. Third, energy conservation, or first law of thermodynamics. First, TD law. Fourth one, second TD law. Second law of thermodynamics. This is first law of mass conservation. This is first law of second law of Newton's equation. Newton's law of second Newton's law of motion. This is first law of TD. This is second law of TD. So students, I will move to the first one, conservation of mass conservation. Mass conservation for a system. System means we are using system approach. I told you there are two types of approach. First one is a system approach or closed system approach. Second one is open system or control volume approach. So in system approach, how will you get an expression for mass conservation? Mass conservation is nothing but m is constant. Mass is neither created nor destroyed. So that's the idea behind mass conservation. So if you are taking a particular a system with a fixed mass, m is constant. That means m does not change for that particular system with respect to time. So with respect to time means dm by dt equal to 0. So this is the equation for conservation of mass for a particular system. Now, how will you define mass conservation? Mass conservation in control volume approach, CV control volume approach. How? If you are taking a particular control volume, so this there may be mass input will be there, mass output will be there, right? So how can you form an expression for mass conservation? So the difference between input and output of mass flow will be equal to change in the amount of mass that is present accumulated in that particular control volume. So students, if MCV is the mass accumulated in that particular volume, then dou by dou T of MCV will be equal to difference between input and m dot out. Why I am using dot over this particular this term? Because dot represent per unit time or rate. Dot represent rate of mass flow. So rate of mass inflow, the difference between rate of mass inflow and mass outflow will be the rate of mass accumulated in that particular control volume. That is how conservation of mass is formulated for the control volume approach. Now I am going to define. So if the mass flow was if the flow was steady, if it was steady flow means with respect to time, no change with respect to time. Dou by dou T of MCV equal to m dot in minus m dot out, right? If steady flow, then this term will be 0 because nothing will change with respect to time. That is the idea behind steady. This gives m dot in equal to m dot out. So for a steady flow, the mass influx, the rate of mass influx will be equal to the rate of mass outflow. Now I will try to get an expression for one-dimensional continuity equation. Continuity equation is nothing but equation for mass conservation. Mass conservation. So I am taking a control volume. I am taking a control volume like this. So let this be a control volume with a length an infinitesimal or a differential volume, a differential control volume with the length dx. Okay, so this is a differential control volume with the length dx. If pressure, if at input the pressure be p, at output the pressure be p plus dp. At input velocity be v, here v plus dv. At input density be rho, here output rho plus dou rho. The area be a at the entry, area be a plus da. Okay, so these are the properties. So these are the various properties at the entry and exit section of this particular differential volume. So students, please note down this figure. Okay, now we have the equation dou by dou t of mcv equal to m dot in minus m dot out, right? How can we define mcv? Mass in the control volume. Mass in the control volume, mass of the fluid within the control volume is the product of average of. Okay, how can we define mass? Mass can in terms of density and area and length, rho into volume, rho into volume, right? Density into volume gives mass. So volume is area into distance x, right? So this is how we write mass in terms of density, area and the distance, the length of that section, right? So in case of mcv, we can use, because the density is different from different in both entry and exit, so we will take the average of the density. Average of density means average of density is rho is that at x inlet, rho plus dou rho is at exit. So the average will be whole divided by 2. So 2 rho plus dou rho by 2 whole by 2 gives rho plus dou rho by 2. So mcv can be written as rho plus dou rho by 2 into, similarly, average of area. You can write d rho itself, mcv equal to rho plus d rho by 2 into a plus dA by 2 into what is the length of that section, dx, right? So you multiply rho a into dx plus you can neglect all the higher differentials. So by neglecting all the higher differential terms, if two differential term, the product of two differential term comes together, you can neglect those. So finally you will get rho a dx. Okay, mcv will be rho a dx. So keep it there. Let it be equation number 1. Okay, or equation number 1, equation d by dt of MCV will be d by dt of rho A dx, right? So since area and dx are constants, they won't change with the time. So only density change with the time. So A dou rho by dou t dx. So d by dt of MCV will be A dou rho by dou t dx. Let this equation be 1. Okay, keep this equation as 1. Okay, now we have to find m dot n. What is m dot n? M dot n means, since this is a dot product, rho A velocity v, not dot product, this is in rate, mass, rate of mass flow. Instead of rho ax, the rho a into length, we have to use velocity. Velocity is length by time, so we have to use rho av, right? Then what will be m dot out? M dot out will be density at outs, the exit is rho plus dou rho, sorry, d rho plus a plus dA plus v plus dv, right? So you have to multiply all these things. Rho a v is the, okay, rho a v is the, and rho a dv is there, rho v dA is there, plus av d rho is there, plus many other terms will be there. They will be higher order terms, so you can neglect those higher order terms. Only these 4 terms will be in lower order, because in higher order terms means in that there will be product of 2 differentials. So product of 2 differential means you can neglect those terms. Okay, so m out will be rho av plus rho a dv plus rho v dA plus av d rho, av d rho, right? And now we have to substitute this m dot in and m dot out in the equation 1, right? So equation 1 becomes how m dot, okay, before that we have to calculate m dot in minus m dot out. So m dot in was rho av minus rho av plus rho a dv plus rho v dA plus av d rho. So these are the terms. So these 2 terms will get cancelled. Finally, m dot in minus m dot out will be minus rho a dv minus rho v dA minus av d rho. Okay, so the equation 1 becomes, what was m dou by dou t of mcv? A dou rho by dou t dx equal to minus rho a dv minus rho v dA minus av d rho. So bring all these 3 terms from right hand side to left hand side. So the equation becomes a dou rho t by dx equal to, sorry, plus av dp by av d rho, right? Av d rho plus rho v rho A dV plus rho V dA equal to 0. Now bring this dx to denominator of this, divide all this equation by dx. So it will become A dou rho by dou t plus AB dou rho by dou x plus rho A dou V by dou x plus rho V dou A by dou x equal to 0. Right. Now since we are our objective was to find an equation for one dimensional steady state flow, right? Okay, this is for a normal case. If we have to find the equation for steady state flow, steady state means we can cancel this term, because with respect to time you can cancel. Then the equation becomes AV dou rho by dou x plus rho A dou V by dou x plus rho V dou A by dou x equal to 0. So this will be the equation for steady state. So this can be simplified into, since this is a product of rho AV, dou by dou x of equal to 0. This means rho AV equal to constant. So if you do the differential of the product rule, if you apply product rule for this equation, you will get this equation, right? So the final equation you are getting is rho AV equal to constant. So this is the one dimensional equation, a continuity equation, one dimensional continuity equation. This is nothing but m dot itself. M dot is constant for steady state one dimensional flow. For steady state one dimensional flow, you can write rho AV equal to constant, right? Now that's it for mass conservation. Now we will move to momentum conservation. Momentum conservation. Okay. So for a system, this is momentum conservation is nothing but the second law of Newton's Newton's motion. There is law of Newton's motion law is there, right? Newton's second law of motion. Do you remember? It's nothing but change in momentum. Change in rate of change of momentum will be equal to force applied, right? So sigma F will be d by dt of momentum. Momentum is nothing but d by dt of mass into velocity. So this is the equation system for system approach. In system approach we can write sigma F equal to d by dt of mass into velocity. For control volume approach you can write sigma F equal to dou by dou t of mv for Cv plus, since there is a flow of mass inwards and outwards of the control volume, there will be m dot v out minus m dot v in. So this is how we write. So the momentum theorem for control volume says that the net force acting instantaneously on that fluid within a control volume will be equal to the change of momentum, rate of change of momentum within that control volume plus what? So this is the rate of sum of just listen once more. The sum of, or the net force acting instantaneously on a fluid within that control volume will be equal to time rate of change of momentum within that control volume, plus plus the difference between momentum flux, the difference between the outgoing momentum flux and incoming momentum flux. So this is the outgoing momentum flux, the momentum associated with the mass that is flowing outside, and this is the momentum associated with the mass coming inside that control volume. Okay, so this difference plus rate of change of momentum within that control volume. Sum of these two terms will these two terms will give all the net force acting on that control volume. So this is how we write conservation equation for momentum over a control volume. So students, now I will try to get an expression for one-dimensional steady flow momentum equation. Okay, so students, let me take a differential, a cylindrical differential element through which some fluid flow is taking place. Now let the this is incoming fluid, this is outgoing fluid. Okay, so the pressure acting at this interface, that is entry PA. Now the pressure acting towards this phase. So this is phase is PdP. So since I am taking a differential volume, the differential volume will be subjected to pressure from both sides, right? Both sides. Since the fluid is flowing through a streamline, so I am assuming fluid is flowing through a streamline, there will be a action of pressure on that particular volume, that particular control volume or particular element, differential element from both sides. So both will be in opposite direction, right? Let the velocity of at entry be v, at the exit be v plus dv. Let the weight of that particular differential volume be dw. Let this area, this particular area be dA. So this area will also be dA. Okay, so this length of this be this section, this differential element be ds. So dA is the cross section area, ds is the length, dw is the weight of the differential element, v be the inlet velocity, v plus dv be the outlet velocity, P acting towards P acting at the entry, P plus dP acting at exit. So the direction of P plus dP will be opposite to P, because the pressure is acting from both sides on that particular because there will be a fluid outside that differential volume also. That volume, that fluid, those fluid will be applying pressure on this differential volume in this direction. So this is our figure. So this is the problem. Now we have to get an equation for momentum conservation. So what are the different forces acting on that? Forces tending to accelerate this particular fluid element. So there will be pressure force at here. Use a reading. Pressure force will be here, P into dA. P dA at this section. Here what will be the P plus dP dA in the opposite direction, so it will be minus. Okay, so there are two forces due to pressure at inlet and exit. Now third force will be the weight of that particular element. Okay, so the weight of that element. Before that, I have to get another point is so this is the streamline. So if perpendicular to this streamline, and if you take this 90 degree, so this will be wait, you take this is the entry point, you extend this is the exit point, so difference between these two, this two will be dz, so take that as dz. Okay, dz, right? So are you okay with this figure? So you can understand if you rewind this from the beginning itself. Okay, don't worry, if you rewind, if you watch it once more, you'll be things will be clear to you. Now you may feel a little bit messed up, the figure may be a little bit messed up for you, don't worry. Okay, now three different forces are first one, difference between the pressure, right? P plus dP into dA. So this will be PdA minus PdA minus dP dA. Okay, so this cancel. So dP dA remains, right? dP dA remains. Now one a component of weight dW is there. dW is means nothing but mass into dm into g, mg. So since we are taking a differential element, so differential mass of mass of that differential element will be dm into acceleration due to gravity. Dm can be written as rho g rho into density into volume, right? Density into volume. How can we get volume? Volume is nothing but area into length, rho dA ds g. So this is the equation for the differential weight of that particular element, right? So this is acting downwards. We require the component of this. So this was the differential element. W is acting towards downwards. So this is dz, right? Dz. So we require P is acting this way here, P plus dP. We require the component of dW in this particular direction. Component of dW in this particular direction. How can we find that? How can the length of this is ds, this length is dz. How can we find that? Just think of it. So students, since this is ds and this is dz, if this angle is phi, so dw is acting this direction, right? So we know the component let this dws, the component acting in that particular direction is dwz. So dwz will be equal to dw by cos y, right? dws cos y will be dw, so dws will be dw by cos y. So this is obtained using our geometry. So how can we define cos y? Cos y is nothing but adjacent side by hypotenuse. So adjacent side is dz. Adjacent side by hypotenuse, dz by ds, right? So students, I think this is wrong. dw cos phi will be dws. Since this is in opposite direction of p is in this direction, p plus dp is in this direction, w is in dw is in this direction, minus dws will be in the same direction of opposite direction of p, so we have to add a negative. So dw cos phi, so dw cos phi is nothing but dz by ds, right? Dz by ds. So now the component of weight in the direction of motion is nothing but rho weight, dw is rho g ds dA into cos phi minus rho g ds dA into dz by ds. So actually if you are taking into account all the three means p a minus p plus dp into dA minus rho g dA ds dz by ds. Here ds and ds cancel, so this already we have done. So remaining is minus dA dp minus rho g d minus rho g dA dz. So these things these are the net force, sigma f. Sigma f is nothing but this one. Okay, so you have got sum of forces. Now you know, now our equation was like sigma f equal to dou by dot t of mcv, sorry mv mass into momentum cv minus m dot v out minus plus m dot v in, right? This was the equation. Since we are considering steady state flow, this will get cancelled. This will get cancelled. So the remaining is sigma f and these two terms. So you have to find the expression for m dot v out and m dot v in. How can we find? So mv, mass into velocity. How can we write mass? So mass is nothing but rho into ds, length into area dA, right? Now mass into dV. So if you have to find m dot, you just add ds by dt. So this will become dV, rho dV dA, right? Now we have to find m dot v out minus m dot v in, right? So m dot v out minus m dot v in is nothing but for outside v, actually it is v plus dv minus inside m dot v itself. So this will get into the form of m dot dv. So m v out minus m dot v in will be m dot v plus dv minus m dot v is m dot v plus m dot dv minus m dot v. So this and this get cancelled. Finally we will get m dot dv. Actually we have m dot means rho dv dA, right, into rho dv rho ds by dt into dA into dv, right? So ds by dt is nothing but d by dt of s is nothing but velocity, rho v dA dv, right? So our equation was sigma f into m dot v out minus m dot v in. So this has become minus dp dA minus rho g dA dz equal to rho dA v dv, right? Now you can divide by dA, whole divided by dA. Equation becomes dp minus rho g dz equal to rho v dv. Now rearranging the equation, rho v dv plus dp plus rho g dz equal to 0. Or dividing by rho, we will get v dv plus dp by rho plus g dz equal to 0, right? So this equation is known as Euler's equation. Euler's equation. So if you, the integrated form of integrated, so dp by rho plus rho v dv by v dv plus g dz equal to 0. This is Euler's equations. So if you integrate this equation, over the streamline, the integrated form will give you what equation? Do you remember? So that equation is nothing but Bernoulli's equation. If you integrate with respect to that streamline, you will get the equation called Bernoulli's equation, where p by rho plus rho half v square plus gz equal to 0. So this equation is Bernoulli's equation. Okay. Now we will move to energy equation. Conservation of energy. Energy equation. In case of energy, the net energy, first law you know, no? The dE will be equal to change in the heat transfer minus work transfer. The change in total energy of a system approach. In system approach, change in total energy of a system will be equal to difference in work transfer and heat transfer, right? So in right form, you will get the d by dt of E equal to del Q minus del W dot. So here you have to put dot. So these two are in right form. For control volume approach, how can you write? You might have already studied in your thermodynamics. I will remind you once more. Q dot, okay, Q dot minus W dot equal to dou by dou T of mass into energy. Energy here, this energy is specific energy, capital E by mass, plus m dot E m dot out minus E m dot in. Okay, So this work is shaft work plus flow work. Okay, shaft work plus flow work. What is flow work? Flow work is nothing but pressure into specific volume. Pressure into dV. So this is known as flow work. Okay. So adding flow work also you can write it like q dot plus, suppose you have I'm drawing a control volume, mass inflow, mass outflow, m dot in. Suppose this is our control volume. We have a mass inlet, m dot in, mass outlet, m dot out, P1 at pressure at inlet P1, density at inlet ρ1, specific volume small v1. Okay, specific temperature T1, enthalpy, specific enthalpy H1, specific energy small u1. Similarly P2 ρ2, small v2, T2, small h2, small u2. Okay. Now let the input be at a length at a height z1. Okay. Output be at height z2. Okay. So we are deriving an equation for steady flow. Since flow is steady, means m dot in and m dot out will be same. We have already studied in. So let it be m dot itself. M dot in is m dot out. For steady flow energy equation, SF is steady flow energy equation. Okay. M dot in equal to m dot out equal to m dot. So we have already studied q dot minus w equal to dou by dot t of m e m cv plus e m dot out minus e m dot in, right? So what is this E? Small e means total energy. Total energy is the sum of internal energy, potential energy and kinetic energy. So E will be sum of internal energy plus kinetic energy plus potential energy, right? Now work is sum of shaft work plus flow work. Okay. Now I have taken a control volume like this. I am adding shaft work. So shaft work is negative. I am adding heat to that particular space control volume. So this will be positive, this will be negative. Now I can write q dot minus w shaft, and actually here work was sum of shaft and flow work. Now I try to keep shaft work here itself and flow work to right hand side. Now I will add here. So actually here, since dou by dot t of m c v m e c v plus m e out minus ME in. Since this is SFEE, steady flow, M remains constant and this term cancel because this is with respect to time. So this will be 0. Now we have to add one more term here, flow work, because here it only shaft work remains, flow work comes to left hand side, right hand side. So I can write Q dot minus shaft work equal to M dot plus E was there. Now flow work is added to it. Flow work is PV. So this is out minus M dot E plus PV at inlet. Now E is sum of, I will make Q dot minus WSH equal to E is nothing but U plus V square by 2 plus GZ on PV is also. So this whole thing is E into M out minus U plus V square by 2 plus GZ plus PV into M in, right? So this will become Q dot minus shaft work equal to what? Out means U2 plus GZ2 plus V2 square by 2 plus P2 V2 into M, right, into M dot, you need M dot here minus U1 plus GZ1 plus V1 square by 2 plus P1 V1 into M dot. So here sum of U plus PV is nothing but enthalpy H. We have already studied. So the equation get even simplified to the form H2 plus V2 square by 2 plus GZ2 M minus H1 plus V2 square by 2 plus GZ1 M, right? Alright. Now I am taking this M common and taking to the left hand side. So Q dot by M minus shaft work by M equal to H2 minus H1. I am simplifying it. I am rearranging it like V2 square minus V1 square by 2 plus GZ2 minus Z1. Okay. So this is nothing but small q and small w. Small q dot minus small w dot equal to H2 minus H1 plus V2 square minus V1 square by 2 plus GZ2 minus Z1. So this is the equation for steady flow energy equation. Okay. If there is no heat and work transfer, the equation will become H2 minus H1 plus V2 square minus V1 square by 2 plus GZ2 minus Z1 equal to 0. So this equation will become H1 plus V1 square by 2 plus GZ1 equal to H2 plus V2 square by 2 plus GZ2. Okay, so this is the case of a steady flow energy equation with no heat or work transfer. So if inlet and outlet are at same level, these two will get cancelled. the equation will even become the equation will become even simpler. Like h1 plus v1 square by 2 equal to h2 plus v2 square. h1 plus v1 square by 2 equal to h2 plus v2 square by 2. Yes, this is steady flow energy equation with no heat or work transfer. Okay, and z1 equal to z2. The inlet, the flow, the entry and exit are at same level. So you have to remember energy equations. We are more we should be more careful about. We may be using this equation more often. Okay, don't worry about momentum equation. Momentum equation won't be used that much often in our coming sessions. But energy equation will be used more often. So you have to remember this equation. Okay. Now the fourth is steady flow, second flow, the fourth one. We have already mass conservation, momentum conservation, energy conservation, and fourth one is second law of TD. That is nothing but entropy change is greater than or equal to dq by dt. A closure statement. Do you remember? Okay. Using the definition of entropy for a system undergoing an infinitesimal process, entropy change ds will be greater than or equal to dq by dt. That is Clausius statement. Okay. So for a particular control volume, you can write over control surface dq by dt should be so you can write like this. If you take the time derivative, dq by t should be less than or equal to system, right? So if you take time derivative, it will become 1 by t of d by t of q less than or equal to d by dt of system, right? So this is system approach. In case of control volume, you can write like this: over the control surface dq dot by t will be equal to dou by dot t of m s small s over control volume plus m dot s out minus m dot s in. So just keep this equation in your mind. This won't be used that often. Okay, so this is the second law of thermodynamics and entropy equation. Okay, so for the time being, I will stop this session. Thank you.